The second presentation is instead focused on how to create tools for optimizing and monitoring the ladle furnace process. Ladle furnace process that basically aims at refining the steel composition and the steel temperature before the continuous casting. So the idea is to related to the process that operators add additional material to the molten steel, steer the molten steel through argon injection, and use electricity and thermal system based on electricity to keep the temperature more or less constant to reach a certain boundaries before the continuous casting. And we developed a tool for monitoring and also optimizing the ladle furnace operation in order to also to improve both the sustainability and the economical impact of the ladle furnace operation. Why we propose this tool? Well, mainly for three main reasons. The first two are, let's say, difficulties in terms of forecasting. So it's difficult to forecast and to control the thermal behavior of the molten steel within the ladle because of the unmeasured heat losses, because of the complexity of the behavior of the thermal distribution, let's say. And second point is difficult to control the chemistry of the molten steel because the complexity of the chemical reaction and the interaction between the molten steel, the additional ferroalloys and also the oxidizers, the slugs that are above the steel, and also the fact that there are delays between the addition the operators make and the measurable effects, because there is a limitation in the sensing in terms of first temperature, because temperature is sampled every more or less 5 to 10 minutes, let's say. But also in terms of chemical analysis, because the chemical analysis, so the operators must take a sample from of the molten steel, bring the sample to the laboratory, let's say analyzing the sample from a chemical point of view, and see what is the current chemical composition of the steel in order to understand what kind of alloys, for example, improve for achieve a specific, let's say, steel quality. Well, our ALCHIMIA software for the ladle furnace aims, let's say, are at analyzing real time, and in fact analyzing real time through artificial neural networks the process data that we receive from the IT system in order to provide an immediate estimation of the final steel characteristics in terms of final steel chemistry and final steel temperature. And also provide an optimization tool that is based on genetic algorithms, another tool, another methodology that is, let's say, in the field of the artificial intelligence that allows to optimize, let's say in this case, processes, behavior, and so on, suggesting a set of additions and operating strategies in order to achieve a certain steel quality, desired steel quality, with the objective of minimizing both economical costs and environmental impacts. The key features of the software are first, the AI-based prediction, so machine learning models that are trained on historical data that estimate the final temperature and final chemical composition. And this allows, for example, to reduce trial and errors in achieving, let's say, more a certain steel quality. Multi-objective optimization for searching, optimizing, let's say, the recipe for producing the steel, the specific steel, aiming at reducing the economic cost and also environmental impacts. And this allows operators to select, let's say, a better strategy for controlling the ladle furnace operation. And we integrated an online life cycle assessment tool that evaluates the environmental impacts for the specific heat. And this allows to monitor the sustainability of the specific heat. Two final key feature, well, a graphical user interface that allows operators to see in a dashboard process data, prediction, and optimization results. This is a decision-making tool, basically. And it's scalable and integrable in the architecture because it can be easily connected to existing supervisor and control system. In other words, so who targets this software? Well, for sure, AIF-based steelmaking, but also basic, blast furnace, basic oxygen furnace based steelmaking route, where the steel must be refined for achieving a specific steel quality. With the idea, particular focus on improving the efficiency and sustainability of the furnace process. Who can be interested on this product? Well, process engineers and metallurgists, because they can use the prediction for optimizing addition and achieving certain temperature. Production managers that are interested in reducing costs and operational variability. But also environmental and digital innovation manager that have a focus on monitoring the environmental impacts and performance of the process. We designed a system for the free salsa plants. In particular, we create models that focused on this system, on the specific plant. We also created an optimization system that focuses on the LCA of the specific plant. The optimization provides some select, let's say, or give some suggestion to the operators in terms of mass of the added materials, so ferroalloys, the oxidizers, and slag formers, the amount of energy consumption for keeping the temperature within the limits, and also the argon consumption in the system. We train the system with around 3,000 hits for each specific plant. And the models demonstrate also in the testing phase, let's say, quite high accuracy and also precision. The optimization allows to have suggestion in around 40 to 50 seconds, so more or less in real time, as soon as operators receive the first sample of temperature and chemical composition. And the optimization system, this is a result that we identified during the simulation, let's say, of the optimization system by using real data. We saw that we can decrease the economic cost of around 6 to 80%, even more for some specific heats, for some specific steel qualities, and decrease the environmental impacts of about 5 to 10% in average, let's say. This is the graphical user interface that we created, so the dashboard where the operators can see the current heat, the current steel weight, the temperature of the steel, the current chemical composition, and the historical set of, let's say, heats, the previous heats. The operators here in this part of the graphical user interface can put, let's say, constraints on the operation of the ladle furnace in terms of minimum, maximum temperature, maximum electricity to use, argon, the prices of the ferroalloys, for example, and the energy and argon. Select the impact, the LCA impact categories that they would like to optimize. And at the end, they receive after 40 to 50 seconds, let's say, a set, you can see in the right, a set of ferroalloys that should be added in the ladle to reach a certain final chemical composition of the molten steel, and a certain final steel temperature. And then they can evaluate the environmental impact if they apply this control operation to the ladle furnace, and so they can evaluate the LCA, the impact, environmental impact of the system, of their production, having also the possibility to export PDF file for the report of the heat. If you would like to know more, well, we publish several papers on this, but also you can see the project results on the website. You can also contact us if you are interested to have a dedicated session for your specific with your specific plant data. And in summary, we can say that artificial intelligence, again, it's a very important tool currently that is showing effectiveness on extracting additional information from the plant data. We integrated several artificial intelligence-based methodology in the prototype to demonstrate that artificial intelligence can be a very important tool for improving sustainability, but also, why not, economical costs in the steel industry, but also outside. And the goal, yeah, in fact, is to provide intelligent tools that provide some, let's say, support the operator. These tools does not, let's say, replace operator. This is important. Thank you. If you have questions, obviously, we will wait for your question at the end of all these sessions.